Thank you. Thank you to the organizers for the invitation. So, topic of this talk is maps between curves. And diophantine obstructions. So, well, let's start with the maps between curves, and then we're going to get to the diophantine obstructions in a bit. So really what I want to do is I have two curves, maybe C, D over K. So K, for me, is going to be a finite field. So some of the stuff that I'm going to say applies to arbitrary fields, but I really want to concentrate on finite fields, and some of the stuff that I will say only applies to finite fields. And I'm interested in finite fields. And so C and D are smooth, projective, algebraic curves. So we're given two curves, C and D, over this finite field, and we ask ourselves the question, is there a map? Perhaps non-constant. So I'll get back to this, whether I want to think of maps or constant, non-constant maps, or all maps, D to C. So I give you two curves by giving you to you by equations somehow, and I ask you, is there a map between these two curves? How do you decide? Well, if you allow constant maps, then the question is not too difficult. It depends on whether C of K is empty or not. So this morning we had a talk about pointless curves, and in fact, pointless curves are quite interesting in this context because the constant maps disappear, and some of the things become more interesting. It's easier to state some theorems when the curve is pointless. When the curve has points, you have to be a little careful with the constant maps. Okay, so how do we decide this? Now, before I get back to this question again, I want to formulate this question in three different ways. So there's three different natural ways to express this question. So first of all, we can consider the set of maps, F from D to C. So we can also consider, so let me introduce some notation. So if you let K be the function field of D, so KD, field of rational functions on D, then this set here is equal to CK, the points of C with coordinates in the function field of D. So a point in C with coordinates in the function field of D is given by functions on D that takes value in C, so you get a map from D to C. So that's second way of viewing this set, and by viewing it this way, I'll bring in some ideas from arithmetic geometry. So this is sort of a diophantine equation, if you like. And the third thing that we can consider, so these are two different ways of looking at this problem. And the third way is to, if we define F to be the function field of C, then we can consider embeddings F into K, right? So if you have a map from D to C, with non-constant map from D to C, you get an embedding of F into K. So this set here is not quite this, is this. So it's maps, so this is a set of all maps, and this is the set of constant maps. So depending on your tastes, you can think of this question as a question in algebraic geometry, maps between curves. You can think of, if you're maybe a number theorist, or a diophantine geometer, you can think of k-valued rational points on C. And if you prefer to think about function fields and you're algebraic number theorist or something like that, then you might want to think of it in terms of embeddings from F to C. And so when I originally planned my talk, I was going to spend most of my time here. But this is sort of work in progress, and I'm going to be talking about a bunch of conjectures, actually. Maybe there's a few theorems that I'm going to mention. The theorems, I think some of them are over here, but the conjectures maybe are over there, and maybe the conjectures are more interested about than the theorems. And I've been thinking about those things, and so what I said in the abstract and not exactly how the talk ended up being planned, but hopefully it will be interesting, and there'll be lots of questions, so you know, people may want to think about some of the questions they're going to raise. Okay, so and I'm not going to say much about this setting, but this question has been looked at, well, been looked at in many different settings. In particular, there is an algorithm. So I could stop the talk here and say, well, this problem is solved, let's go home, to decide if there is a map, or even non-constant map, due to Florian Hess and Moman. So Hess had an algorithm. So a special case of this problem is to decide if the two curves are isomorphic. So a special case, you know, if you have two curves, how can you decide if they are isomorphic? And Hess provided an algorithm that given two curves, find out if they're isomorphic and find the isomorphism between the two curves. This algorithm is efficient and practical. It's implemented in Magma. So Florian went to Sydney and wrote it up in Magma, so it's there. So you can plug into curves and ask if they're isomorphic, and it spits it out very quickly. Moman was a student of Hess who wrote I think a master's thesis kind of thing, where he extended the algorithm to look at this more general question.
What is the curve for your computer in this case? What is the data, the input?
Equations, maybe. Okay, so give a curve in projective space. So that's the input. Or the function field of the curve, if you like. Which probably is the same thing. Now, there's one caveat, is that this algorithm is, so if you want to think in these terms, in terms of function fields, is a search. So you bound the height of the point, so you bound the degree of the map by using the Hurwitz formula. Oh, by the way, okay, maybe I should say, so let's assume C has genus greater or equal to 2. I mean, the case genus 0 is trivial, right? Or, you know, there are lots of maps. And genus 1 is not so interesting. I'll answer the case of genus 1 and in passing later on, but the genus 1 is less interesting. So, and then, so if the genus is at least 2, then the Hurwitz formula gives you an upper bound for the degree of the map, if there is a map. And with that, you turn into a finite search. Because if you use the factor in finite field, then things become very easy. You can just, if you fix a point in C, there's only finitely many possibilities for the pre-image of this point, because it has to have degree bounded by the degree of the map times the degree of the point. And so you can crank it out. So this algorithm is efficient. Well, it's an algorithm that searches for the map. And in a way, it will find the map, and if the map is relatively simple, it's going to find the map quickly. The problem is, if there is no map, this algorithm may be running for a long time. We know that it's eventually you run out of possibilities and you decide that there is no map. But really, what I want to focus on is how do you decide if there is no map? So is there a good way, quick way, without actually trying out all the possibilities to rule out, the existence of such a map. So want to focus on proving that there is no such map. Okay, so that's my goal, is to present you some ideas of showing, so given two curves C and D, is there some kind of way that, without actually trying to find all the maps, to rule out the possibility that there's a map between C and D? Okay, so here is a first idea that was going to get. Before that, let me mention. So yesterday, was it yesterday? Ivan gave a talk about mentioned maximal curves. So there's this thing of these new curves, these new maximal curves, the Giulietti and Koshmaros and a few other new maximal curves, and they are interesting because they're not covered by the Hermitian curve, or not covered by Ree and Suzuki curves in characteristic 2 and 3. And so this is an interesting example of a situation where you want to show that there is no map, right? So these curves are interesting if they're not covered by old curves. So you have some new maximal curves that are not old curves. And so actually in those cases it's fairly easy. You show that you compute the possible degrees of the map, and you show that the target curve has too many points. So one thing that you can always say is that if there exists f from D to C and the degree of f is m, so non-constant, then the cardinality of ck is greater or equal to the cardinality of dk over m, because the map is m to 1 at most. So you have that. So if you violate this condition, then you show that there is no map. In particular, so if cardinality, well, of course, so if cardinality of ck is bigger, is less than the cardinality of dk over m, then there is no map. In particular, if the cardinality of ck is 0, if it's a pointless curve, and the cardinality of dk is positive, so if D has a point and C doesn't have a point, of course you have no map, right? If D has a point, this point has to go to a point, rational point of C. So there is no map. In this case, there even isn't a constant map either. So that's one way to rule out points, rule out maps. And we want to take this idea a little further. So one thing that you can try and do is count points. So there's one thing that you can do sometimes, if you have a curve, is count the number of rational points. That's in some situations easy, and there's some experts in the audience that tell you how to compute points very quickly. Over there, how many? Lots of them. So we're going to count points, and we're going to use the point counts to rule out maps. We could do this. We can also use the zeta function. So let me define LC of t is the numerator of the zeta function. Can do the characteristic polynomial for Frobenius on H1 or whatever. Okay, so we use that notation. Does that work? I guess it works. Okay. So if you have a map F from D to C, you have pullback of divisors induces a map F upper star from the Jacobian of C to the Jacobian of D, exhibiting the Jacobian of C as an isogeny factor of the Jacobian of D, and that implies, so non-constant, that implies that the L function of C divides the L function of D. Right? So here's the criterion. The criterion to decide if there is no map. So if you're able to compute the L functions, and the L function of C does not divide the L function of D, you know that there is no map. Now Everett has given examples of curves, distinct curves with isomorphic Jacobians. So this is not enough, right? You know, so not even to distinguish isomorphism. So we need to do something else. Okay, so here's. So I want to take a little detour and explain a little bit about the fundamental group and then come back to this idea here. So let me talk about the fundamental group of a curve. So the tau fundamental group. And quickest way to define it for curves is to take the Galois group of so pi 1 of C is the Galois group of the maximal unramified extension of K. K, F. F is the function field of C, right? So you take all the unramified extensions of C, which are Galois, you get a bunch of Galois groups, you take a projective limit to put them all together, you get this big group, which is called the fundamental group of C. And it encodes a lot of information. In particular, it encodes the L function. So how do you read off the L function? So you have a map. So I'm not going to define the fundamental group of an arbitrary algebraic variety, but you can imagine that such things exist. And you have a map, and it's functorial. So you have a map from pi 1 of C to the pi 1 of the Jacobian of C. And let me tell you what the pi 1 of the Jacobian of C is. So a tau covers of, maybe I should say one thing about the fundamental group, is that you can take geometric extensions. So you can go to the algebraic closure and then start taking geometric extensions, and you get a subgroup which is called pi 1 of C bar. This is a base change of C to the algebraic closure of my constant field, and it's a subgroup of pi 1 of C. So this is sort of like what you learn in topology. So this is the fundamental group. Well, it's not quite, but it's related to the topological fundamental group. And it has a quotient, which is the Galois group, the absolute Galois group of little k. So this guy here fits in an exact sequence like that one, and the pi 1 of the Jacobian of C bar is a product of Tate modules. Huh?
Are you choosing a rational point in C here?
No, I can't choose a rational point because of the,
No, for the map.
For the map, no, I'm not, I will. Let me.
What is this map set from?
Well, you choose a rational point and you define. No, you choose a divisor degree 1. All you need is you just need an effective. You just need a divisor degree 1.
Okay, but you're choosing that. Okay.
Yeah, yeah. To get this map, you have to choose one. So this fundamental group is a product of Tate modules, and the way you get the extension, so to get an extension like this, you have to define an action of this group into this group. This is a semi-direct product. So if you have an action of this into this, you can build this up. And the action is the Galois action. So the Tate module, the Galois action of the Tate module determines the L function, right? So the Galois action just tells you how Frobenius acts. Once you know how Frobenius acts, you can take the characteristic polynomial and you get the L function. So this guy here, and this is surjective, and I don't know why I'm writing zeros because these groups are non-abelian. Well, this group is abelian, but well, this group is abelian. This group is not abelian, but okay. So this guy here is just the product of all the Tate modules with the Galois action. So you can read off the L function of C from that. And what does the rest tell you? Well, one thing that it tells you is not only the L function of C, but the L function of all the unramified covers of C, because the fundamental group is built up of unramified Galois groups or unramified covers. So this guy has a lot of information about.
I mean, it's one of the major open problems in Galois theory to find I1 C bar.
Yes.
Any projective smooth curve other than a projective line.
Yes. And so this group is not known. This group is not known for any curve of genus 2 or more. So what she's saying is that, you know, I'm not going to get very far by looking at this. You know. So, but what I want to do is take something out of this. You know, all of this is something I cannot compute. So, you know. But there's some information there that I'd like to use. Now I got lost. Hang on a second. What do I want to say? Okay, so what I want to do is I want to look. So, like she pointed out correctly, this thing is not going to tell you much unless you can produce some Galois covers. One way to produce Galois covers is to produce abelian covers. So class field theory at least tells you what the abelian covers are. And now remember, so class field theory kind of abelian covers of C will tell you come from the Jacobian, so you're getting this information back again, but what you can do is take an abelian cover and then take the L function of that abelian cover. That will require abelian covers of the abelian cover. So you're actually doing a two-step solvable thing. So that's what I want to do. So I want to take abelian covers and take the L functions of the abelian cover. So let me define an abelian cover. There's one that comes for free. And in defining it, I'm going to answer Bjorn's complaint about embedding the curve in the Jacobian. So let's choose a map, embedding C into the Jacobian of C. So what do we need for that? We need a divisor of degree 1. Okay? So you have to make a choice, and once you make a choice, then you by functoriality you get this map. Okay. Now I have C inside of the Jacobian. I want to take a cover of the Jacobian, which I can get, for example, by taking an isogeny from the Jacobian to itself, and then I can pull back. So I want to choose one nice isogeny. So I'm going to choose identity minus Frobenius. That's an isogeny. The kernel of this isogeny is the rational points of the Jacobian. And I get a curve here, which is the pre-image of C under this map. So this is I minus Frob upper star of C, which I could call the Hilbert class field of C. It kind of isn't, and it kind of is. So the problem is, you know, the Hilbert class field, you have to choose a divisor, an irreducible divisor, a place, and then you can define the Hilbert class field of the things where the place splits. And this is sort of correspond to choosing the embedding. So this guy is not uniquely defined, but it's well defined up to a twist. So all the choices of the embeddings give you different choices for this age of C, which are the same up to twist. So they're all isomorphic over an extension of the ground field. Okay? So I want to do that. And now I can come back to, yes, that's where I lost my plot there. I wanted to state why I was talking about the fundamental group if it's completely useless. The whole package is completely useless. Because there is a theorem due to Mochizuki and Tamagawa that if pi1 of C and pi1 of D are isomorphic, and let me put an asterisk here. So isomorphic means, so the fundamental group sits in that exact sequence that I wrote on that blackboard up on top there. And when I say they are isomorphic, I mean an isomorphic that preserves the exact sequence. So it's an isomorphic of the middle thing that comes with an isomorphic of the left thing and the right thing, and everything commutes. So that's what I mean by isomorphic star. Then C and D are isomorphic. So if we could compute the fundamental group, we could solve our problem. But as we can't, that's not going to give us. But solve the problem of the isomorphism, the subproblem of isomorphic. So there isn't at the moment, as far as I know, a corresponding statement for maps. Although there is a theorem like this in the number field case, which is due to Mochizuki, that says that if there is an open map from pi1 of D to pi1 of C, open in the sense that sends maps open sets to open sets, these things are profinite groups, then there is a map of curves. I don't think this is proved in a finite field case, which is kind of surprising. So there are some things that are not true, so you have to be careful. So for example, in the finite field case, the section conjecture, if you know what I mean, is not true. So, and section conjecture will classify constant maps. So there are some things that you have to be careful with. But that theorem is true, so you should be able to decide, if you could compute those two groups, then you could decide if these two things are isomorphic. But you can't. So maybe, but you can compute this, I think. Can you? This is my first question. So how computable is this? For small finite fields, I think it's reasonably computable. For big finite fields, you have to compute Jacobian. So I want to use this. So let me use this. Okay, so where am I? So I don't know. So when I was writing this talk, I was hedging my bets, and I stated, I wrote a conjecture. So hedging my bets and making conjecture, it's not really does make big sense, but okay. So conjecture, C and D are isomorphic. If and only if so I'm going to write something and then I'm going to erase it. So maybe you're going to be upset with me, but there you go. So that's what I wrote in my notes. C and D are isomorphic if Hn D is Hn C is the same as Hn D. What's Hn? So iterate this process. So take so age 1 is as age, and age 2 is age of age, and so on. But I'm feeling bold, so I'm going to state this. Okay, so some justification for this conjecture. So if it's false, there should be a small counterexample. Okay, so people who have databases of curves should run your... So find two curves that are distinct with the same, for which the L function of the Hilbert class field is the same. And when I mean the same, I mean up to twist, right? So there is a twist. So this curve is not well defined. So when I say this, I mean there's a twist of this guy that gives me the same L function as this twist of that guy. So they have to match. Yes?
Could you just use the pick one instead of pick not, and then not mess around with the twist? Like use the allo map to put C into its
Yeah, but so then what's the map? Peak 1 is not an abelian variety. So I don't have isogenies. I think I have to make up some choices. Maybe there's a way of being canonical about this, but I'm not sure. So why this conjecture? So we know the birthday paradox. The birthday paradox states that the probability very close to 1, there's 2 people in this room with the same birthday, right? Maybe you can check. Now the birthday non-paradox is the following. I'm willing to bet a lot of money that there are no 2 people in this room who were born in the same day, month, and year, the minute and second. Okay? So there are 2 people in this room that were born in the same year, same month, same day, and same minute, and same second. Unless, of course, you know, the Conrads are in the audience or something like that. So this is obvious, right? So if you have a map from a small set to a huge set, with large probability this map is going to be injective. And so when you take L functions, you're computing, the L function characterizes the Jacobian of the curve up to isogeny. If you're just taking the L function of the curve C itself, you're just looking at the Jacobian of C up to isogeny. And if you are over a small genus, the number of isogeny classes of abelian varieties of that dimension is smaller than the number of curves of that genus. So typically the map is not injective. So the map is not injective in small genus when you take curve mapping to isogeny class of Jacobians. For large genus, then you get a chance that the map is injective, and I guess it's not known what's really happening if 2 curves of large genus can be distinguished by their isogeny class of the Jacobians. But now this guy here has a huge genus because the kernel, so what's the degree of this map? Is the number of rational points in the Jacobian, which is kind of something like Q to the G. If K is FQ, then that's the degree of this map. So the degree of this map is huge. So this curve has a huge genus. So the isogeny class of its Jacobians, set of isogeny class of Jacobians of that dimension is enormous. So hopefully they'll be distinguished by the L functions.
Huh? I mean, it's not always enormous.
Huh?
There are some Jacobians.
What?
There are some Jacobians that don't have a huge number of points.
Yes, but so here comes. So there's a good point. So there are 8 curves. 8 curves. There's 8 curves, such that the cardinality of the Jacobian is 1. So there's 8 curves of class number 1, for which that map there is the identity, and for which HC is C. Well, so that, yes, but it was wrong. So yeah, so they found 7, and recently some guy found that there was an 8th one. But I think this is right now. Well, you know, I can't guarantee 100%, but you know, yeah. So there are 8 curves. Well, certainly there are at least 8 curves with Jacobian with class number 1. And what happens to this? So I checked. So for those 8 curves, the L function of the curve itself is enough to distinguish the curves. So this theorem is true. This conjecture is true for curves, for those curves, 8 curves. but you know, that's perhaps the most dangerous case. So I'm good. Oh, maybe you're not. Maybe you think I'm too optimistic. All right, so I have one more example here. So let me write down this example. So, where is it? Okay, so it took me a lot of effort to find two curves with isogenoous Jacobians. I should have written to average. This is two curves over F7. So these are two curves over F7 with isogenoous Jacobians, so their L functions are the same. The curves are genus 2. Now, this curves, the polynomial on the right splits into three quadratic polynomials. So there's three double covers that you can take of this curve. When you take those double covers, so you have C prime is a double cover, unramified double cover. So this curve has genus 3. The Jacobian of this curve it splits up to isogeny as the Jacobian of this curve plus an elliptic curve. So we can work out what the elliptic curve is. So there's three elliptic curves. Each of these two curves gives me three elliptic curves. And you compute the trace of Frobenius, which will determine the L function and the isogeny class. And here you get all of them with trace 4.
Should there be a 6? Should that be x to the 6th?
6, yes, thank you. And this guy here, two of the covers, so there are three covers that we can take, three double covers. Two of them also have this isogeny factor, which is an elliptic curve with trace of Frobenius equal to 4. But the third one has trace of Frobenius equal to 0. So this curve cannot be isomorphic to that one, because there's no way that, well, not even up to twist, so. Okay, so that is for isomorphism. Where is my conjecture? Is up there, here. Okay, so what would you do for maps? Well, we can try. So I'm going to ask this as a question. So, question. So assume. So now here for this question, I do have to exclude the curves which there's 8 curves that have class number 1, because you don't get anything else by taking the ages, and you don't expect to get an obstruction out of this cover. So assume that the cardinality of Jacobian of CK is not 1. Does LHN CT divide LH? So maybe I should write it as. So apply this Hilbert class field n times dt for all n greater or equal to 1, imply there exists f from D to C non-constant. So here I do need to not just look at the Hilbert class field, but the Hilbert class field, 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 and so on. But so you get the characterization, but this is going to be hard to compute. So apply this functor many times is going to get prohibitive. But I wanted to have something with L functions that I had some hope that it would be true. Okay, I don't have a lot of time, but I wanted to talk about the other kind of diophantine obstructions that are more sort of number theoretic. So let's talk a little bit about the Hasse principle. So what is the Hasse principle in this situation? So if C of capital K is not empty, then C of capital KV is not empty for all V places of K, right? So we know that that's a true fact. What does that mean? Well, this guy, so KV is the functional field of the curve D. For this to be non-empty is enough that, so for this to be non-empty is enough that C of little kV is not empty, where kV is the residue field of D, of V in D. Place. So the Hasse principle, so the local obstruction to the existence of rational points that those guys are not, is fulfilled if C has a point over every field for which D has a point. Right? Every finite field. So yeah. So because it may not be that. So if D has a rational point, you have to require the C have a rational point. That's enough. If D doesn't have a rational point, but say have a quadratic point, then you want C to have a quadratic point as well. So that's the product of C K V is not empty if and only if for all fields L over K finite such that DL is not empty, we have CL not empty. Right? And of course this is a necessary condition for there to be a map, non-constant map from D to C. So this is sort of a local global obstruction, and it's become a thing these days in number theory to look at refinements of the Hasse principle. And one refinement of the Hasse principle is the finite descent obstruction. So I want to talk about finite descent obstructions. And so how does this work? So if you have a tau cover, so you have my C here, and you have an tau cover X, and if you have a point P in CK, so this is tau Galois, this implies, so we call it pi. So if you have a rational point, it implies that there is a twist of x prime, mapping to C. So a twist of the cover, such that, and a point, so maybe we call it a pi prime, if this is pi, and P in x prime of K, pi prime of P equals Q. So, if you have a rational point of C and a cover of C, there's a twist of that cover for which this rational point lifts. So, and that gives you an obstruction, because if you can show that none of these twists have rational points, then you show that C doesn't have any rational points. How can you show that not all of the twists have no rational points? Maybe they don't have local points. And so that's an obstruction to the existence of rational points, is to consider covers, twists of covers, and trying to find some cover for which all the twists, so none of the twists have points. That seems like a complicated thing to do, but in fact it's very practical. Like Niels will be able to tell you how practical that is, right? So we can try and do this here, and it turns out, well, so I think that finite descent obstruction should obstruct the existence of rational points, and here's a theorem. So I was hoping to talk more about this, but I don't have a lot of time. So this is not known. Well, so So Bjorn and I proved the theorem that is like that this thing works, but unfortunately it's for non-isotrivial curves. So if you have a curve over capital K that is non-isotrivial, then you can try and do the same thing, and in fact it works. But here in our situation we are in the isotrivial case, so our result does not apply. But I have a theorem that finite descent obstruction works not for rational points, for integral points. So if you have an affine curve, you can talk about integral points, and sort of something similar happens on, not for all curves, but on modular curves. So modular curves are curves, in characteristic peak that are defined over a finite field. So this is an example of a situation that we can do that. So for integral points on modular curves, you can decide whether they exist or not. So this would be a map from a curve to a modular curve. So you have some modular curve, I don't know, x of n or x naught of n or whatever, and you have some curve d, and you want to study maps from d to this curve, but with a fixed set of points here being mapped to the cusps. So that's the integrality condition. So you're going to have to fix a set of points in here and require that these points map to the cusps. And then you want to, is there such a map? And then you can decide that by doing descent. And you can do descent by taking covers that come from putting additional level structure. So that's a cheap way, is a canonical way of getting covers of modular curves, is by adding primes to the level. And that works. So that sort of suggests to me that maybe finite descent obstruction is works. So if a curve survives, if C, all the covers of C admit a twist that has a point over K, yeah, we have local points everywhere, then there is a global point. And one last thing, because I'm almost out of time, I wanted to mention, so maybe I'll write it here. This twist is defined, so this twist is another curve which is isomorphic to x over an extension. Now, if you're looking for global points, the extension that untwists it has to be unramified in this situation here. In the situation of isotrivial curves, the extension of k that untwists x prime is unramified over k. So it's a cover of D. So if you have if this thing is, if you don't have the obstructions if you don't have finite descent obstructions, for each cover of x of C, each cover x of C, you end up producing a cover of D. What is this? Is a map from pi 1D to pi 1C. So, don't have time to give the details, but if there is no local obstruction, no finite descent obstruction, then you get a map from pi 1D to pi 1C. So this finite descent obstruction is sort of stronger than the condition of the fundamental groups. So earlier in the beginning, we were looking at conditions of fundamental groups, but finite descent obstruction is stronger. And so again, because we cannot compute these fundamental groups, we cannot do finite descent obstruction with all covers. We're going to have to restrict to some covers, and it's a very good question that I could give another talk about. Which covers do we take? So which covers are good for computable and will likely to obstruct and which ones don't. But fortunately, I ran out of time, so I'm going to stop here. Thank you.
Comment. You might want to, for those people who haven't sort of thought about this sort of thing before, you might want to remind people who haven't, or point out to people who haven't thought about this before, that this has a lot to do with de-randomization of, like, right, factoring polynomials over a finite field is efficient and randomized in a randomized way. But if you could solve some problems like this in some effective way, that would de-randomize that.
I didn't know that, so thank you.
Thank you.
Maybe I should find out more about this.
Any more questions? Just a moment. What did you...
My question is really short and really stupid, so I don't know if it's worth your walk.
Too late.
What if you, so like I minus Frobenius is going to be really annoying for large P. If you want to actually, what if you just use like multiplication by 2 or something?
Yes. So I'm not confident enough to state the conjecture. And so one thing that I do know is that if you, so there are counterexamples if you look at multiplication by powers of 2. So that's not enough. So you're going to need more. So typically, I mean, usually it's going to work.
Is what's good about this just that it has a huge degree, or?
Yes. So you want things of.
What if you just took Frobenius?
Frobenius is inseparable, so
okay.
It's not going to do you anything. Yeah.
Thank you very much. Any further questions? If not, then let's thank the speaker again, and we reconvene in 5 minutes at 5. Thank you.